Okay, so let's talk about just sort of how we're going to get started analyzing our spectrum, specifically by looking at the molecular ion peak and then the base peak. Remember, base peak is just a fancy way of saying the largest peak in your spectrum. Okay, so first of all, note that for some compounds, the molecular ion peak is the base peak. So for example, benzene is that nice, stable aromatic. It does not fragment very easily. So our base peak is our, this is both the base peak and the molecular ion fragment or the parent fragment. That's not the case for something like pentane, which does fragment much easier. Here, the base peak is this fragment here, and the molecular ion peak is much smaller down here, meaning that most of it fragments. Okay. Importantly, though, the mass of the, in both of these cases, the molecular ion peak has an m over z of, in this case, 72. And that corresponds exactly to what you would expect given the molecular formula, right? That's the beauty of the molecular ion peak. Corresponds to the mass, the molar mass of the, actually, more correctly, the atomic mass of your compound. No. I guess it wouldn't be atomic mass because it's not an atom. Whatever, molecular mass of your compound. Likewise, over here, the m over z is equal to 79, which you would expect from the formula benzene C6H6. Okay, so there's so much information in that molecular ion peak. Yeah, I guess we are going to say molar mass. Okay, so the m over z of the parent ion, or that molecular ion, is equal to the molar mass of the compound. That is the number one most important piece of information that you're going to get from your mass spectra. And again, it seems like how much information is that really? Well, it turns out to be a lot because of what we were talking about last lecture about how our molecular formula tend to fit those nice, neat little patterns. Okay. Another good piece of information, easy piece of information you can get right off the bat is that if you have an odd mass molecular ion peak, it means that there are an odd number of nitrogen atoms in that molecule. Okay, again, talking about organic molecules here, but it turns out that nitrogen is one of the few atoms that you're going to add that's going to give you an odd number molecular ion. Now, if you have an even number, you either don't have any nitrogen atoms or you have two nitrogen atoms. Okay, and that might seem like, well, how the heck do I tell the difference? But again, if you take these, if I told you that you had a saturated organic molecule that may or may not contain nitrogen, and it had a molecular weight of 74, you can play around with those numbers and determine that there's really the only way that you can add everything up is to have two nitrogens in there. So that was one of the reasons why building that calculator before at the end of last lecture was really important, because it's going to take a bit of playing with numbers here. You're going to be adjusting numbers in your spreadsheet until you get that right magical number you're looking for, and then double checking that that fits one of those correct molecular formula patterns that we saw. Okay, but again, I think the easiest big takeaway here is that if it is odd, you can be guaranteed that it has one or some odd number of nitrogens. We're going to be dealing with relatively simple compounds. There's not going to be like 17 nitrogens in there or something like that. Okay, so now let's talk about fragmentation again, right? Because that's something easy that you can see just by looking at the molecular ion peak. But if we look at, the spectrum of pentane again, let's just go back and look at this real quick. Notice how we have these like clusters of peaks here, right? Here's a cluster around our molecular ion peak. Here's another one. Here's another one. Here's another one. Here's another one. Those correspond to losses of carbons and all the hydrogens that are attached to that, right? So we had our molecular ion peak at, what was it, 72? at 72. That first big fragment that we saw was at M minus 15, or 72 minus 15 is what, 60, 57? Is going to be centered around 57, and that corresponds to the loss of a methyl radical. So let's check that out real quick and make sure that checks out. And indeed, this guy right here is 57. Okay. Likewise, in the next chunk over, we have the molecular ion fragment minus 29. So that 29 corresponds to this ethyl radical that popped off. Okay, so this would be, that would be 43. And again, 1, 2, 3. We have this, our base peak is that M minus 29 or 43, M over Z equal to 43 fragment. So our base peak corresponds to the loss of an ethyl radical. And this chunk right here is the charged part that hits the detector. Remember, it's only the charged parts, the charged fragments that correspond to the detector. So the reason why we see those clumps of peaks is because we're losing bigger and bigger segments of our molecule are being chopped off as radicals. Okay, so this is something that you're going to see often in your mass spectrum. What are the other ones going to be? All right, so here's the breakdown that we just saw. What are these other peaks going to be? Those are just spaced one apart. Those are going to be the loss of individual hydrogen atoms that are falling off. Okay, so, and again, you don't really know just by looking at pentane that the, you know, molecular ion minus 29 or that 43 peak is going to be the largest one. Okay. However, there is some information that you can get if you're comparing similar spectrum. And for that, we have to remember about carbocation stability. In fact, the most important thing that's going to determine why one fragment is, you know, the base peak or has this high intensity versus another fragment that has a lower intensity is because of the stability of the carbocation that's formed. Remember that this is the trend in carbocation stability that we've seen before. Methyl carbocations do not really like to form, whereas tertiary carbocations and allylic carbocations are very stable, and, you know, secondary in the middle there. Okay. Another consideration, but way less important, the most important one is the carbocation stability. But there's also this another aspect, which is the radical stability, which trends actually very similar to carbocation stability. So if you can form, for example, a secondary radical and a tertiary carbocation, that would be great. Okay, so this is what sort of putting rhyme to reason as to like why these molecules fragment the way that they do. So for example, if we had something like this molecule below, we would expect that the tertiary carbocation fragment at M minus 43 to be quite big compared to if this was a straight chain. All right, so this is what I mean. You're not going to know just by looking at a molecule all the different peaks that it's going to fragment, but you can get an idea of what some of the bigger ones can be. And this is going to be especially important when you're comparing very similar spectra. So let's look at these two here. We have two different mass spectrum here. And this is, I know that things get really intimidating here, but bear with me. We have two different spectra here. One, it corresponds to pentane, so just the straight chain 5 carbon. And the other one is going to correspond to 2-methylbutane. Notice that both of these are going to have the exact same molecular ion fragment at 72. All right, so we're not going to be able to narrow it down just by looking at the molecular ion fragment. That's definitely the first thing we look at all the time, but we're going to have to dig a little bit deeper here, okay? What you want to notice about 2-methylbutane is it has this tertiary carbon, which means that when it fragments, it's going to become a secondary carbocation. And there's actually two different ways that it can fragment and form a secondary carbocation. The first way is if this portion here becomes a fragment, and the other half, or the charged carbocation fragment, and the other half becomes the radical. So I mean, I'm going to chop this bond here. This portion becomes a radical, which isn't detected by my detector, but this is my secondary carbocation that forms. Well, this would correspond to an M over Z of 43. Okay, and then I have another fragment that I can have, which is also a secondary fragment, or a secondary carbocation, which is if this chunk here breaks off and forms my charged carbocation. So that means I'm breaking this bond here. This is a methyl radical and a secondary carbocation. And so this is going to have an M over Z of 57. We would expect that the 2-methylbutane would fragment in such a way that the M over Z at 47 and the M over Z at 43 would be larger than just pentane. Well, if you look at 43, it's actually the base peak in both of these. So that's not the greatest way to determine. But this spectrum down here has a significantly larger M over Z at 57 than does the top one. We can conclusively determine that this is 2-methylbutane on the bottom, and this is pentane at the top. Okay, so again, it's not that we looked at this molecule and was able to say, oh, I know exactly how it's going to fragment. But if we're comparing two structurally similar molecules, the difference being, one's got this is tertiary carbons or even quaternary carbons, we know that those are going to fragment into more stable carbocations, and that can help us sort of pinpoint what's what.